Let's begin Chapter 10, Inferences Involving Two Populations. Chapter 10 consists of three kinds of two-population inferences. Number one, when we have paired data, that is, when we have two completely dependent samples. In this case, we simply take the differences between one and the other and consider a new sample given by the differences. That's going to be the easiest case, and that's covered by 10.2. And then we consider two independent samples. Depending upon the mean or the proportion, we have to use related but a little bit different techniques. And those are going to be discussed in 10.3 and 10.4 respectively. Finally, in 10.5, we talk about variances and standard deviations. And that's going to be an advanced topic. Depending upon circumstances, depending upon semesters, that could be considered as an optional topic. By the way, this is a continuation from the previous chapter when we discussed the chi-square distribution. Okay, let's resume our discussion in my notebook here. And section 1 of my notebook summarizes 10.1. What about the dependent data, paired data from one sample, like pre-test scores and post-test scores of a certain class? How about independent data? Well, test scores from two different classes or two different sections. They are completely unrelated, and we can consider those as independent. In some cases, we may have correlated data. In that case, things are a little bit tougher, and we do not really deal with those kind of things here in 1000 level. We did discuss some regression and things like those early on, not more than that. By the way, here's a checklist. And here we go. This is kind of roadmap our textbook author gave us. Begin, and here's the first question. Does the inference concern the mean? Yes, then what kind of sample? Dependent or independent? Depending upon the answer, you have to use different technique. 10.2 technique or 10.3 technique. The key difference will be the standard error formula for 10.3. And then, if it is not a mean, then is it about population? Is it about proportion, excuse me? In that case, we cannot use t-distribution. We'll use z-distribution, and we have to do that for relatively large sample size, n value 100 or bigger, usually. And that's going to be discussed in 10.4. And finally, if it is about standard deviation or variances, then we have to use this f-distribution, which is a continuation from chi-square analysis of the previous chapter. Okay, let's go to 10.2 now. Two dependent samples. And this single line, this one line summarizes entire 10.2. If we have two dependent samples, we simply take the differences. And then we consider the mean and standard deviation of the differences. Turns out that mean of the difference is difference of the means. But for standard deviation, we don't have that nice formula, so we'll have to recalculate the standard deviation for all the differences. And then we do exactly the same as before, as we did in chapter 9. That's it. That concludes 10.2, and then let's go over to 10.3. Or, no, I was just kidding. Let's do an example here. Actually, a couple of examples. First example is about estimation. Let's find out a confidence interval. 10 subjects with borderline high cholesterol levels were randomly selected for a study that involved taking a nutrition education class. Cholesterol readings were taken before the class and 3 months after the class. So pre-class we have these cholesterol readings, and then after 3 months we have these readings. Now what do? We simply take the difference between one and the other. And then here are the differences. Most of the subject here had some drop in cholesterol level. But for example, subject number 4, well, this person actually had higher cholesterol level after class. So the education class did not really work well for this person. But for these kind of people, 70, 75, or 55, with these kind of people, it worked pretty well. Now we have to consider the confidence interval. We can find out, oh, I want this picture, this table again. I want to find out the mean of the difference, which will be the best point prediction, and then we can find out the confidence interval from there. By the way, if we simply subtract from pre-class minus post-class or post-class minus pre-class, doesn't make too much difference except for sign, plus or minus. So let's just take this one and then go from there. Okay, how do we do that? Well, here's the solution. Typical thing, we have the sample size of 10 and we have these data, and then we do exactly the same as before. There are 10 subjects, so the sample size is n, and consequently the degree of freedom is n minus 1, so that's 9. And then the mean of all these, and that turns out to be 24.5. If you simply add them up and divide by 10, you're going to get that. And the standard deviation or sample standard deviation is a little bit trickier. You'll have to calculate the deviation squared plus deviation squared and so on and so forth, and divide everything by n minus 1, and then take the square root. A little bit complicated, but here we go. Mathematical's computation is kind of like this. And then the standard error is standard deviation over square root of n, and it is calculated like this. Detailed calculation is left to the students. Let's find out the 95% confidence interval. How do we do that? The first thing we should do is draw the normal picture and put the center point, which is the mean. Okay, kind of like this. 24.5, that goes right in the middle, and we have this kind of normal picture. And then we have 95% in the middle. Consequently, toward our left, we have 2.5%. Toward the right, we also have 2.5%. So what do? Take the normal table and then look up 2.5% and then find out appropriate t-score. As a matter of fact, excuse me, we are looking for t-table, so it's going to be a little better if I take the right-hand side. Let's open up the t-table. Okay, here we go. The degree of freedom is 9, and then we are looking for 0.025, 2.5% to the right-hand side. This is a t-score, 2.262, and that's to the right. To the left, you're going to get negative of that. And that's how we get where's the solution? Yes, this solution here, t-score. Let me get this picture here. Okay, copy and paste this picture. And from this picture, what do? N minus center over standard error is a t-score, and consequently this number or that number, let's call those either x minus 24.5, the center, over standard error 9.14 something, is a t-score 2.262, but we have negative 2.262 as well because we have the symmetry. All we have to do is to solve this linear equation, and it can be done rather easily. Flip the denominator to the other side, calculate, we get the left hand side endpoint and we get the right hand side endpoint. So what do you get? Here is the confidence interval between 3.14 to 46.86. And this is a visualization, by the way. Okay, now how about a little bit more difficult problem? Let's go over to the next problem here, hypothesis testing. Same paired data, and here's a question. Is there sufficient evidence to declare that this nutrition education class helps people reduce their cholesterol levels? Set up appropriate hypotheses and test them with the significant level of 1%. Okay. We have to set up the hypotheses first. And hypothesis is typically, the null hypothesis in this case is typically 0, no difference. In some cases, the problem may explicitly ask you the difference is bigger than 25 or something like that. But if it didn't say anything, then for paired data, we are always comparing with 0. And there we go. No significant difference. Mean difference is 0, is my null hypothesis as we have here. And then we had a little bit of improvement, as we saw, 24.5. Is it big enough? Well, alternative hypothesis is significant improvement, greater than 0 or significantly greater than 0. By the way, these statistics are the same as before. The detail is left to the students. Okay, now here's the initial picture. Draw a t-curve, and then what goes right in the middle? Is it 24.5? Well, 24.5 was for the confidence interval. For hypothesis testing, we have to do it with respect to the null value, 0. Kind of like this. 0. And we want to find out this critical value. We have 1%. Alpha is 0.01, so this red area over here where my mouse is moving around is 0.01, 1%, and this blue part is 99%. And with that, we can find out this critical value. Once this critical value is found, you can compare this one with 24.5, the observed mean. If the 24.5 comes to this blue region, then that means close enough to the null, so null hypothesis wins. If 24.5 comes to the right hand side here in the red region, then too far away from the null value, so alternative hypothesis wins. All depends upon this critical value, and let's find out. The usual method, end minus center over standard error, is t-score. Let's go ahead and do that. End minus center over standard error, and let's get that picture again. And okay, this x value, critical value, and center is 0, so we have 0 over here. And the standard error we calculated, and that should be the t-score. By the way, what's the t-score? Here we want 1%, so yes, 2.821 approximately speaking. So that goes right here, and what do we get? We have this linear equation to solve. Flip the denominator to the other side and solve for x, and what do we get? We have 26.634. 26.634. And the observed mean was 24 point something, wasn't it? Observed mean difference was 24.5, yes. And the critical value is 26.634. So what's your conclusion? Here we go. Null hypothesis wins. Rejects the alternative hypothesis and accept the null hypothesis. 24.5 belongs to the blue region. I'll leave the probability method to the students. I believe that's relatively less important and a little bit more difficult to follow.